So all of these particles are called subatomic particles because they are smaller than an atom. They're the particles that make up an atom. So there are three significant subatomic particles that chemists care about: protons, neutrons, and electrons. There are other particles, but we're not going to cover them. So protons and neutrons have nearly identical masses. These masses here you might need to use in a homework problem, but you definitely do not need to memorize them. What I'd like you to note here is that they're both times 10 to the minus 27 kilograms. And so if we look at this number at the beginning of the scientific notation, 1.67262, 1.67493. So the difference comes in the fourth significant figure. They're very, very similar. The mass of an electron, significantly smaller, almost 2,000 times smaller, 9.1 times 10 to the minus 31 kilograms. So again, to give you an idea of relative sizes, the proton would be like a baseball. The neutron would also be like a baseball. And then the electrons would be like grains of rice. So much, much smaller. Well, let's look at this. I told you last week that when we measure things, we like to use a unit that is similar in size to what we're measuring. So a kilogram is not a good unit for measuring the size, the mass of a proton, because we end up with this crazy, crazy small number. And so we could use metric prefixes and make smaller and smaller units, but even we run out of metric prefixes, they just don't get small enough. So we made up a unit. And again, all units are made up. So this unit is called the atomic mass unit. It's not very creative, but it is very descriptive. It's a mass unit for measuring the mass of an atom. It's abbreviated AMU, and we pronounce that AMU, not AMU. So 1 AMU is 1/12 the mass of a carbon atom containing 6 protons and 6 neutrons. So this carbon atom has 12 of these massive particles in it. And so an atomic mass unit is 1/12 the mass of that. So what that means is the mass of a proton or the mass of a neutron, very close to 1 atomic mass unit. The charges, so the electron is the fundamental, the smallest piece of charge you can have. The charge of the proton and the electron are equal in magnitude, opposite in sign, so that when you have a proton and an electron, they get together, their charges add up to 0. And the neutron has no charge. So these are some things that we should know. So the proton has a mass of 1 atomic mass unit. I don't care if you know, you don't need the 727 part. And its charge, its relative charge is +1. The neutron also has a mass of 1 atomic mass unit, and it has 0 charge. The electron has a mass of approximately 0. For many purposes, we can just forget about its mass, and its charge is -1. So highlighted there, those are things you should know. Protons and neutrons are located inside the nucleus. The electrons are outside the nucleus. So usually matter is charge neutral, doesn't have a charge, because you have equal numbers of protons and electrons. But charge imbalances are possible. And when those imbalances occur, it's not stable, and the imbalances tend to resolve themselves to equalize, sometimes in very dramatic ways. And this is where lightning comes from. So lightning comes about because we have positive charge that builds up on the ground and negative charge that builds up in the clouds. And the lightning is a result of the equalization of that charge. The thunder is the noise caused by that equalization. Static electric shocks are another example. So, on a dry day, you shuffle your feet on the carpet and then you go touch the metal door jamb and you might get a little shock, right? Or you take a balloon and you rub it on your hair, right? And you see little sparks, right? That's electric charges that got separated and now they're going back together. So protons are important.